Okay, thank you. I'll get started. Hello, my name is Mark Freeman. I am a member of 50 by 30 Niagara and Biodiversity and Climate Action Niagara. I'll be your host for this webinar tonight on sustainable home cooling with sustainable home heating and cooling with zero emission buildings, or in plain English, we're going to be talking about heat pumps instead of using natural gas to heat and cool our buildings. I'd like to thank you all for joining tonight. And after a few opening remarks, our guest speakers will be talking more about heat pumps, specifically ground source heat pumps for geothermal geo exchange solutions, as well as the more common air source heat pump for typical home use. If you have any questions for today's speakers, please type them into the chat and we'll ask your questions during the question and answer portion of the webinar after the presentations. If you prefer, you'll also be able to raise your hand using the react button that's at the bottom of your screen, so you'll be able to ask your questions verbally. As Liz said, this webinar is being recorded, and we will send out this recording.
So, my name is John Rathbone. I'm the CEO of Rathco ENG, as well as Overview, which is a software platform that we're using to accelerate the decarbonization of the built environment. We're a 7-year-old company. I used to work for a Danish-based engineering company and got some really nice trips to Copenhagen out of that deal. And my job was to essentially be a conduit for over 50 years of study and modeling and design and implementation of district energy systems. So over in Denmark, over 70% of homes and buildings are heated with district energy systems that are fueled with low carbon fuels. So that's kind of how I got into this world. And I saw an opportunity to kind of do more here in North America. And that's when I took that opportunity to start Rathco ENG. So district energy, we'll get to in a second, is just a form of thermal distribution. And we realize that the market here in North America needs a lot more than just one solution. A lot of the times I go into a client's office and they're like, John, I have 5 problems. And if you're only here to solve one of them, you're really not that helpful. I need you to solve at least 3 of my problems. So we got into generation. And the way the market was looking about 7 years ago, to me, it was painfully obvious where we were headed as a society in terms of decarbonization. And I really did not want to build a business around being a horse and buggy expert at the advent of the Model T. So renewables are the Model T. And so we decided we're going to become experts in all of these things. And I'm happy to say we've successfully accomplished it. So we are now leading the GTHA in terms of engineering services for renewable energy system design and modeling and feasibility work, specifically around geo-exchange, which we'll get into, district energy systems, but we also do a lot of work with air source heat pumps. We're getting more experience with wastewater energy exchange systems, biomass, which is a very misunderstood form of renewable energy, and industrial waste heat or heat recovery is another way of looking at it. So taking heat from data centers or other types of industrial processes where heat is considered a waste product or a nuisance, that's gold to people like us who are trying to use that heat to decarbonize buildings and directly displace fossil fuels. Before we get into the technologies, I learned some hard lessons over the last 17 years of my engineering consulting business. So when I first started, I graduated from engineering and I thought, wow, I really have a decent understanding of the physical world. You know, I got my physics and my math and my thermodynamics, and I'm going to be able to solve so many problems. And boy, was I naive. So then I started working for the Danes and I got access to the business model of not only how these types of projects are financed and funded, but also the business model of engineering companies, which allowed me to start my own company. And then I naively thought then, oh, wow, I now know how to engineer things that have investable business cases. Like there's going to be a lineup out front of my office of people that want to hire me to do all this stuff because I'll have great technical solutions and investable business plans. And boy, was I wrong again. And I couldn't figure out, you know, what is going on. Like I have all the technical and financial solutions. And then I realized I was missing the most important piece of the puzzle, which was us, people, humans. So there's 3 layers to feasibility is the way I like to explain it to our clients. There's the technical layer, there's the financial layer, and then there's the human layer, or I just call it people. And we have to go through the 3 layers And because the first one, technical, there's probably a few dozen different things that we could do to decarbonize buildings, technically speaking. You're not going to want to pay for all of them. So the next layer is, okay, of the long list of things that are technically possible, which ones make business case or good business cases? So if you're going to invest money into this, is this something that you're going to lose money on? Is this something you're going to break even on? Or is this something you actually could make money on? And believe me, that does exist out there. But then the third layer is people, and this is where culture lives. This is where psychology lives. This is where fear of change lives, and a whole bunch of human biases. So before I get into the bias, I'll just tell you a quick kind of like where I had a eureka moment, and it was working for the Danes, and it was get to know your colleagues, but I was literally the only Canadian that worked for them back then. So I was doing this all over Skype for Business. This was long before Zoom and Teams and all this other stuff. And we did the whole yeah, you're married, kids, and what's your career like and all that kind of stuff. And then it was like, well, what is your energy systems like over there? And they said, well, John, 70% of our country is heated with district energy, and we use biomass and energy from waste as the primary sources of heat to put into those district energy systems. And I said, wow, Jens, that is so cool. You'll never have that happen over here in Ontario. And he's like, but John, they're technically sound solutions and they have really great business models. And I was like, well, yeah, Jens, but good luck convincing a local politician to get behind one of those types of projects. And even if you could, there would be people protesting outside, against those technologies. And then it was my turn to go. And I said, well, here we do a lot of work with heat pumps. And he's like, oh, that's really cool. You must have a lot of like wind and solar in your grid to get the carbon emissions down in the electricity you're using in those heat pumps. And I said, actually, it's because we have a lot of nuclear. And he goes, oh my goodness, John, that's so cool. You'd never have that happen over in Denmark. And I was like, but Jens, it's really sound technology. The CANDU reactors, like we export to our allies, our technology, and they're sound business cases. Like France is building them like they're going out of style. And he's like, but yeah, John, good luck convincing a politician to get behind a nuclear power plant here in Denmark. And even if you could, there'd be protesters outside. And that's when I realized that has nothing to do with the technology or the finances. If you have to focus on making sure that people understand what these technologies are, you have to understand the culture that they are coming from, that they were brought up in, what their biases are, what their business cultures are like. There's so many other more complicated variables that go into this type of stuff than just thermodynamics. But I want to explain to you kind of the three big biases that we run into when we're doing our type of feasibility work to try and get people to embrace these types of renewable technologies. And they're the choice overload bias, the optimism bias, and the status quo bias. So very quickly, the choice overload bias, you all experienced this when you went to a restaurant and it had 6 pages on the menu. And you're just like, oh my goodness, like, what do I do with all of this? Like, I don't know. And what do you do? At least what I do, I go right for the burger and fries. That's my business as usual, right? So I'm like, I'm not going to read this whole thing cover to cover. I'm just going to go to what I'm familiar with, what I'm comfortable with. That's my burger and French fries. And that's essentially what the choice overload bias is. No one's really challenged the engineering or building community to do anything other than natural gas boilers up until very recently. And there's no direct substitute. So there's no technology that I can say to a client of mine, instead of a natural gas boiler, just take this technology and it performs the same from a technical perspective, from a financial perspective. It's same pipes. It doesn't exist. There's always some sort of other types of complexity there. And there's a list. There's not just one thing. There's a list of things. I just listed them, right? So then they just get this, I don't know which one to pick. I don't know how to evaluate them. I'll just go back to my business as usual. Let's put another natural gas boiler in. And then this gets compounded with the optimism bias, which is what's another natural gas boiler? It's really not that big a deal in the grand scheme of things. And don't worry, the government's going to regulate this at some point, and then they're going to force it all to go renewable. And I don't really have to be accountable for my decision making. It's no big deal. It's going to be fine. The next Elon Musk, he or she, they'll be born next week, and they'll invent the new thing, and it's all going to be fine, right? And so that's like the optimism bias and the choice overload bias kind of feeding off each other. But the biggest one that we find is the status quo bias, and that essentially is human beings have evolved to be very good at evaluating and scrutinizing the new thing. So if you're building a home or you're building a big apartment building and you put it natural gas boilers in your building for the last 20 years of your career quite successfully, and then this guy named John Rathbone shows up to your office and says, hey, you should really take GeoExchange super seriously. You're going to have a lot of questions for me and you're going to be very skeptical, and you should be, because that's natural. Like there's a lot of people out there that want to sell you things that maybe aren't in your best interest. And so you're going to scrutinize it. You're going to evaluate it. You're going to, want to hire somebody to model it for you and prove out its business case. And every single renewable has trade-offs. There is no free lunch. Everything has pros and cons. And so when you do this evaluation, you're going to find all the cons with a GeoExchange system, and you will be correct. And then you're going to go running back to the business as usual on the false assumption that the business as usual is the safer thing. And so at Rathco, we've made it a policy that when we do pre-feasibility studies, that the business as usual is a mandatory scenario that has to be modeled and evaluated to compare to the renewables. Because when we do all the renewable modeling and math for our customers, we get a lot of light bulb moments, a lot of eurekas, a lot of, oh, wow, I had no idea that this was the way that this performed. And it's performing quite well, both technically and financially. This is great. But the numbers where my customers' eyes bulge out of their heads is when I show them the business as usual numbers. No one's done the math as to what the true cost of ownership of owning a natural gas boiler is over its full life cycle, because why would you? It's the business as usual. No one asks these questions in the business as usual. And so the only way to really combat this is to model the business as usual to the same level of rigor and analyze it and criticize it in the same way that we do with all the renewables. And then most of the time, our clients make the right choice just purely on the fact that they're really trying to say the business as usual is really ugly and unattractive. This geo thing, let's do it. And once they do one project, they go, wow, that wasn't so bad. And look at my operating costs. They're like, it's so low. Okay, next year in our real estate portfolio, let's do 2 projects with geo. And now we're at the point where some of our customers, like the whole portfolio, we're not even looking at natural gas anymore. And we're finding that this evolution takes about 2 to 5 years, depending on how many projects they do a year. So let's get into technologies. That's kind of like the human layer. I know you weren't expecting an engineer to talk about psychology and biases, but there you go. So another big thing that we found is like, and we were just at Gil and I were just at another conference on Tuesday, and I asked, and it was all about district energy. And we spent the whole day talking about district energy. And at the very end, we had breakout sessions, and I was voluntold into presenting my team's kind of conclusions for the breakout session. And I just had a spidey sense. And I just said, please, just wait a second. Can anyone raise their hand? Who in this room, and there's about 150 people in the room, how many people would feel comfortable standing up at this podium and explaining what district energy is to the rest of the room? The whole day was about district energy. Guess how many people put up their hand? 8. So we're just expecting people to do things completely differently. And most people don't even know what these things are. So when we talk about heat pumps, people don't realize that their refrigerator is a heat pump. Air conditioners are a heat pump. These are all heat pumps. We're really just taking advantage of this thing called the refrigeration cycle. And don't worry, I'm not going to go down the thermodynamic rabbit hole. No math, no science, none of that kind of stuff. But you just need to understand that us nerds, like this, we just look at that and we're just like, oh, it's all the same thing. We're just using it in different ways with slightly different technology. But from a thermodynamic perspective, it's all the same thing. These are all heat pumps. And what a heat pump really does is it just moves heat. It's this really complicated device, but it does something that's really simple. It just moves heat. And unfortunately, in our education systems, we're not really taught about how heat works until you take your second year courses in mechanical engineering, because that's when I was first introduced to this. We need to get it much lower in the educational tree here. So heat moves always. It's a law of the universe. If you could figure out how to break this, you'd be a trillionaire and win a Nobel Prize. But heat always moves from the hot thing to the less hot thing. Always. That is the fundamental principle behind a heat pump. So what a heat pump does is it makes one thing really hot and one thing really cold. And that way the cold thing can absorb heat. Like in an air source heat pump, it can absorb heat from outside, and then it boosts it up to the hot plate. And then your home can then absorb the heat out of the hot plate. And so what it's doing is it's creating this opportunity for the heat to always flow from the hot thing to the cold thing, and then from the hot thing to the cold thing. And now we're able to take heat from outside and move it into your house. And then when we turn it into an air conditioner, all we're doing is reversing that process. It's the same process, but we call one an air conditioner and one a heat pump, and one a refrigerator and one a chiller. But it's all the same thing over and over and over again. So that's how an air source heat pump works, essentially. You might be wondering, John, how does an air source heat pump work in winter? Like, how do I get heat when it's -5 degrees Celsius out of there? And there's another little thing they don't teach you until you get into thermodynamics university, which is there is no such thing as cooling. So there's only heat. I just think of the Ghostbusters phrase, right? There is no cooling, only heat. In the universe, and this is how we look at things from a thermodynamics perspective, there is a floor for temperature. It's -273 degrees Celsius. So you can't get anything colder in the universe than -273 degrees Celsius. But there is no ceiling. So stars, they can go thousands of degrees Celsius. So when it's -5 out there, I actually have well over 265 degrees worth of heat still in -5 degrees Celsius air, believe it or not. So all I have to do on my hot plate, cold plate heat exchanger is make the cold plate lower than -5. So if I make that cold plate -20, I actually can pull heat out of -5 degree air and have it go into my -20 plate, boost it up to like 40 something, and then have that 40 something transfer the heat into your space to get it to a nice comfortable 22. And that's essentially how an air source heat pump works in a very simplistic way. I can expand on this another time. So what we do is we then take this heat pump, and instead of using the air as our source, that's what air source means. We're using the air as the source of pulling heat out of that and putting it somewhere else. We can use the ground. So the types of systems that we engineer are called vertical geo-exchange systems. And so the reason why we want to drill a hole anywhere between 600 and 850 feet down, we don't go that deep for single family homes. If you're doing a vertical, it's probably in the 200 to 300 foot range. But the reason why we want to go down there is that the temperature of the source directly influences the efficiency of that heat pump, and the efficiency directly influences how much electricity it consumes, which directly contributes to how much you have to pay your local distribution company. So if we can make that heat pump more efficient, you will get the same amount of heat for less money. And one of the best ways that we can make that heat pump more efficient is to make the source a better source. And so the air changes temperature by the hour, which means the efficiency and the cost of operating that air source heat pump also changes by the hour. But if we can access the heat beneath our feet, then we can have a much more stable and consistent source of heat, essentially. Now, so that's all we're doing is we're just sending down really cold water into these loops beneath the ground. The water's not going into an aquifer. There's no contamination. We're not pulling water from the ground. We're not pushing water into the ground. It's really just a cold pipe with no holes in it that's absorbing the heat from the bedrock into it. And then we're using that heat pump to put it into the building. But what a lot of people don't understand is that a geo-exchange system is not a true source of energy. It's actually a big, humongous thermal battery, which means I can exhaust it. I can deplete it. So if I am just taking heat continuously out of the ground and I'm not putting it back in, eventually I'm just going to slowly lower the temperature of the bedrock beneath your building to a point where I freeze it. And now it's basically useless as a heat source. Your heat, it'll just fail, essentially. And this has happened to people that don't know how to operate these things properly. So you might be wondering, okay, John, that's great. How the heck do I get the heat back in the ground then if I pulled it all out of the rock? And remember when I said there's no such thing as cooling? That's how we put the heat back in. So in the summertime, when you need cooling, we're not actually cooling, we're removing heat from the building. I know it sounds really argumentative and annoying, but that's literally what we're doing. We're not cooling your building, we're removing heat from it. And instead of just blowing it out the window, we put it back into the ground. And so when we're designing and modeling geo-exchange systems, we're monitoring, well, we model it first, but then when they're operational, we're monitoring how many megawatt hours of heat have we pulled out of the rock in the wintertime, and then how many megawatt hours of heat are we pulling out of your building and putting back into the rock in the summer. And we want these things to be relatively the same so that we can try and keep your bore field balanced, essentially. We can do some really fancy stuff and like engineer them to be imbalanced on purpose, but that's like next level. We'll save that for another day. But the point is, we really want to keep these systems balanced, and therefore the ideal situation above ground in your home is to have a balanced home or building where the building roughly needs the same amount of heating and cooling across any calendar year, essentially. And so that's what we're essentially doing when we engineer these types of systems, is we're trying to figure out what does your building need with heating, cooling, domestic hot water, all the things that typically are using natural gas, and how big can we make the bore field to do as much of those heating loads as possible while maintaining a thermal balance. And then whatever's left over, maybe you need a little bit more cooling, maybe you need a little bit more heating. Then we figure out, okay, the stuff that the bore field can't do, then we can engineer and figure out what's the secondary technology or the companion technology. So we're talking typically bigger scale when we do these things. We're not talking about single family homes, but I think it's just important for everyone to understand, heat pumps, especially ground source. So here's some examples. This was one of the first ones we did 5 years ago. This is now a fully operational building. It's two buildings. We're about 500,000 square feet. We did 115 boreholes at 850 feet, about 15, 20 feet spacing, just kind of laid out in a simple grid. And we did this with our friends at GeoSource, who are one of the best drillers in the country. And so this was a really great first project for us. But then we said, okay, let's go next level. This is a retrofit. So you might be wondering, John, how do you do a retrofit with a GeoExchange? Like, did you shove a drill rig into the basement? Like, how did that work? Well, GeoSource has these really cool drill rigs that can angle the mast. And so what we did is we put them in the parking lot beside the building and then angled the mast at two different angles. We did a 15 and a 25-degree angle. And then we did some really fancy geometry and kind of fanned that out. So it kind of created like a sine wave of boreholes underneath the existing building by drilling beside it. And this allowed us to put enough GeoExchange bore field underneath the existing building, as well as enough capacity for them to basically build a sister building beside it that was twice the size of the first one. So we put enough bore field capacity under this one building for three of it, and then they built the other two, and they're just finishing up the construction of the other two. So we did 113 boreholes. About 80 or 90% of them were the angled ones, and then we were able to sneak in a couple of vertical ones in the corner of the lot as well. We can take this down to a much smaller building. I don't like rules of thumb, but rule of thumb for GeoExchange systems is anything north of 100,000 square feet for these types of deep, they're not really that deep. I'll explain that. But at like the 850 foot range, 100,000 square feet plus, like 9 times out of 10, it's going to be a slam dunk. GeoExchange is going to make a lot of sense. And that 50 to 100,000 square foot level, we're in the kind of it depends category on some of the variables. Maybe the geology needs to be very favorable for us. Maybe the type of building loads need to be favorable for us. And anything less than 50,000 square feet in the real estate sector is a bit of a struggle to make the business case work for this. With that said, there are people doing vertical boreholes for large country homes. There's a whole other kind of industry that's serving that right now. So don't never say never, I guess, is what I'm trying to say. Now you might be wondering, what if we have multiple buildings? Oh, well, this is where it gets even more fun. So this is where I get to take all my experience and knowledge I gained working for the Danes with district energy. And now we can take multiple bore fields and multiple buildings. And instead of putting pipes vertically, we start to connect those with pipes horizontally. And we're able to then do a lot of really interesting things with energy sharing and with peak sharing. So if one building needs heat when the other building needs cooling, we can then start to connect those with very little energy in order to enable that type of sharing. It also allows for more attractive business models because maybe there's 200 boreholes you need for that one building, but you only need to drill 180 because it's going to get the capacity from its neighbor. So this is where we can have it gets a lot more complex, but we like complexity. And you can do some really interesting things when you start to combine district energy with geo. And then this is like, you can just go big with this stuff. So this is one of the biggest ones we've done to date. This is under construction as well. This is 650,000 square feet, 190 holes at 850 feet. And another one that we're doing that's also quite significant, where it's a huge podium deck, and then there's 3 towers built on top of it. So we just put like one big bore field underneath, and a big mechanical room, and it's going to be able to serve all three towers. So really interesting stuff that we're doing right now. So this is not science fiction. This is happening right now. It's a huge part of our business. So district energy system. We just talked about how we're able to use heat pumps to take heat from the bedrock beneath our buildings and then bring it into our buildings and vice versa. But district energy allows us to share energy or move energy. So when you think about district energy, sometimes it is discussed in the same vein as a source. It's not a source. It is distribution infrastructure. So think of district energy system like the wires for our electrical system. Wires don't make the electricity. They just move the electricity. The power plant makes the electricity. So the renewables are like the power plant, and district energy is like the wires, essentially. And so we can then scale things up. Like I said, in Denmark, 70% of the country is heated with this. Children are raised and have lived whole lives and have their own children and grandchildren, and they don't know what a furnace is. Think of that for a second. So really interesting kind of, you start to learn about the cultural impact of what this infrastructure it does when you start to have it for a long time. So district energy, we're doing this right now for the Downsview Airport. I don't know if you've heard of this project. This is insane. This is going to be close to 60 million square feet. It is the old Downsview Airport. It's the last 520 undeveloped acres left in Toronto. It's the only black spot in the city skyline when you're flying into Pearson at night. And it's owned by the federal government. And so they said no natural gas. And we're helping them figure out exactly how to do that. And GeoExchange with district energy is exactly how we're doing that, essentially. We're just taking everything I just talked about and just scaling it up. We're talking bore fields that are like 600 holes and like multiples of them. And we're talking, instead of like dozens of meters of district energy pipe, we're talking about kilometers of district energy pipe. So we can really take this type of stuff and scale it up. And we're totally not intimidated by this, because I just keep looking at the Copenhagen system and we're still itty bitty tiny compared to them. So if they can do it, we can do it as well. And then this one, I don't know if you've heard of ZB. This is the very first big district energy project that we got 6 years ago. This kind of put Rathco on the map. This one is completely net zero. So district energy, if you think about it, the pipes are just filled with water. And so water doesn't care what makes it hot or cold. It's just going to absorb heat and release heat. So in this case, we're absorbing heat from a local industry. There's a Kruger, like I think they make toilet paper. And I don't know how to make toilet paper, but I just know that in the process of making toilet paper, there's a lot of heat that they use to do that. And they just dump it into the Ottawa River, like not the pollutants, but like just the hot water part. And so we built a heat exchanger to intercept that heat and then capture it, put it into the water of the district energy system, and it's piped out to all 4.5 million square feet of this development, providing all the domestic hot water and all the space heating. And then we did kind of the opposite. We put heat exchangers in the buildings to absorb heat, so when they want cooling, and then we just dump that heat back into the Ottawa River. So there's a big intake at the central plant. So it's a really great demonstration project for Canadians as to how we can use district energy and the local energy sources that are around us. We're in the tendering phase for this project right now. This is out in BC. So yes, we do also work in BC. We're across Canada at the moment. This one is using air source heat pumps. So if you've ever been to Kamloops, that's where this is. It's a beautiful place. I highly encourage you to go there. But their geology wasn't that good for geo. They didn't have a nice wastewater trunk sewer going by that we could tap into. They had no industry. It's a campus in the mountains, which is gorgeous, but there's no industry around there with heat production. But they have a really clean electricity grid, and their losing my words here, their climate is very temperate. They don't get the same types of winters that we do. So actually, an air source heat pump at scale makes a ton of sense for them. So we're using two types of heat pumps. We're using an air source heat pump. So we're taking heat, remember the kind of hot to cold of the heat pump. So we're taking heat from the air, putting into water. But then we take another heat pump that's a water to water heat pump to boost it even further and get it up to the temperatures we need for the district heating system. So phase one is going in the ground this spring. We're now interviewing the contractors to install this. There's going to be about 3 kilometers worth of district energy pipe that goes in here. And again, this is going to be completely net zero when it's all done in 2 years. So Thompson Rivers University is going to be completely net zero before 2030. This is another project I don't have any stats for yet. We just secured this one, but the brand new mega hospital in Ottawa is partnered with the same people that are doing the ZB project from a district energy perspective. They liked what we did with ZB. They brought us into this project as well. But this is going to be another great example of using district energy and the local renewable energy resources that are nearby to completely displace natural gas. The hospital is just the beginning, though. Hospitals consume a huge amount of thermal energy, and they make a really great what's called anchor customer. So you can build a business case around having a customer like a hospital be the purchaser of your heat because they're not going anywhere and they're good payers. So you can build a really kind of get started with them, but we're sizing the pipes for 24 inches. These are big pipes. So the plan is to be able to position this facility to then catch all of the new high-rise development that's going to be going in around this hospital over the next 30 years. And instead of connecting to the local gas utility, they will connect to the local district energy utility with zero carbon heating. And last but not least, we're doing a really great project in Oakville. It's all TBD, but I just want to tease this one. I'm really excited about this because Oakville has been trying really hard to get this going, and I think we had a breakthrough. So Oakville is going to be doing something in the years ahead, and it's going to be using a massive trunk sewer as well as some geo-exchange systems, which are very complementary. So what you're going to need to do if you're looking to do a project like this with the region of Halton or Halton region of Niagara or any developers that are looking to do mid-rise or high-rise projects, they're going to have these types of questions. They're not going to know what to do. They're used to hiring the people that did their natural gas boilers for the last 30 years. So we're here to help them and answer all their questions. We can do free renewables 101 workshops, like a long form of this. But what they're really going to want are the outputs that we develop and model in our pre-feasibility studies. So here's where the rubber hits the road with the decision making. We can model out their project for them and tell them, remember, we got to do the business as usual. So this is what your minimum code building looks like because they need to know how ugly that looks with the numbers first. But then we can tell them, here's what an air source heat pump solution looks like. Here's what a ground source heat pump solution likes, and any other sort of the renewables that I mentioned on the second slide tonight. So we could look at biomass, we could look at solar, we can look at all the above. And what we do is we take the total amount of capital cost, so that's like the sticker price of all the stuff, but then we model out a cost model over 30 years or whatever life cycle they want us to do. So we're able to capture all the operational costs, the maintenance costs, the fuel costs, recapitalization costs for like maintenance and that kind of stuff. And then we also do all the energy, and that way we can break it all down to one number, a dollar per megawatt hour number. And that way we can take apples, peaches, pears, and plums and give them a way to do apples to apples comparisons. And then they can take that number and compare it with the GHGs and make a much better decision all on their own once they kind of have the information in their hands. And then we can also then break it back out again and say, okay, here's the operating costs, here are the capital costs for these different scenarios, because some business models have no problem spending more money up front, but really like small operating budgets. Municipalities are kind of like this a lot. And then developers are a little bit more sensitive on the capital, but they're okay with slightly higher operating costs. But we can help figure out the engineering and the finances to kind of find the balancing point for them. So I think that's it for now. Thank you for taking the time to listen to me. Welcome back, Mark.
John, thank you so much. That was amazing. And Mark, I think you're back now. To anyone who came a little bit past 7, Mark is leading this tonight, but his internet quit on him 2 seconds after we started, and he managed to get back on. So I'm going to be quiet now, and Mark, I'm turning it back over to you.
Yes, thank you very much. I apologize. It's bad timing for my internet service provider to reset their network. I apologize for that. Thanks for going forward. And John, I apologize for not giving you a proper introduction.
It's all good.
To make up for some time here, I'm just going to go through quickly a couple of slides. I did want to mention that the reason why we're here is because residential and commercial buildings are the third largest source of greenhouse gas emissions in Ontario. And they're responsible for about a quarter of the province's total greenhouse gases. So we can change that with sustainable building, heating and cooling, utilizing heat pumps. And thank you, John, for that amazing discussion on geothermal. Sorry, I should say geo-exchange and district energy. It certainly appears to be the right way to go when we're looking at large buildings and even communities and complexes like that. So that's great. Thank you very much. Um, the Okay, I had some examples here. I'm not going to go through those. I will mention, though, that we do have a few ground source heat pump examples in Niagara. I'm not going to go through them for time purposes. However, I will mention that McMaster University is heating and cooling its new greenhouse with emissions-free geothermal energy, and I think this is something that they're they're really providing a good prototype for the greenhouse growers in the region. And with that, our next speaker is Gil Amdurski. He's a program manager with the Toronto and Region Conservation Authority. Gil is an experienced sustainability professional with over 15 years of expertise in project management, energy resource, and climate action. He's currently program manager for the Sustainable Technologies Evaluation Program at the TRCA. Gil holds a certificate in renewables energy from the University of Toronto and a diploma in electromechanical engineering from George Brown College. He's a certified energy manager and measurement and verification professional and actively contributes to various industry committees and initiatives. So with that, Gil, I will ask you to take it away.
Sure. Thank you very much for the introduction. 1 second here. All right, is this okay here? Great. Let's just skip an outline. I don't need to talk about what I'm going to talk about. I'll just talk about it. So hey, my name is Gil. I'm coming to you from the Toronto and Region Conservation Authority, representing two different programs. So Mark mentioned STEP, so the Sustainable Technologies Evaluation Program, part of TRCA, so we're nonprofit. We're a highly collaborative group. We conduct a lot of research and education and training. We have this location here, which is out of the Courtright Centre for Conservation, which is really close to Canada's Wonderland, by the way. I know this is Niagara focused, but just throwing it out there. This is kind of a show home that was built close to about 15 years ago now. It's a semi-detached to really showcase sustainable development and green building practices. Throughout the years, we've kind of used the house as a laboratory. We've had close to, I would say, 15 different mechanical heating and cooling systems that we kind of, bring in and take out, gas absorption, air source heat pump, geothermal, both horizontal and vertical. We have solar PV, we have energy, battery storage. Funny enough, we had what I could maybe say is one of Canada's first cold climate air source heat pump all the way back 15 years ago. And funny story, when we asked Mitsubishi for it, they were like, sorry, what do you want with that? So just to say this stuff has been around for a long time, wasn't so common. It is a lot more common now. I also represent the SNAP program, which is the Sustainable Neighborhood Action Plan. And this is very much a boots on the ground, community driven program that has a number of different elements and focuses on key action areas. One of them being energy and GHG reduction, but also urban agriculture, eco landscaping, stormwater management, flood resiliency, and so on. So I want to get into it a little bit. Not going to beat you all over the head with this. I know John mentioned he wasn't going to go into thermodynamics and then started talking about absolute zero. So I caught you, John. But basically, energy has to come from somewhere, right? Essentially, all of it is star stuff. It's from the sun. I'm not going to get too much into that. But it's important to think that all that energy comes from somewhere. We can't actually create energy. We're just moving it around. So I'll ask, an open question of the audience. Wood. Where do trees get their energy from? I don't know if anybody wants to answer. I'll pause for a second. Anybody know where trees get their energy from?
Everybody's muted, so you're going to have to answer.
The
Yeah.
sun.
It is the sun, right? Yeah. So we have photosynthesis, we have leaves, we've got that sun that provides the energy through photosynthesis. We rip carbon out of the atmosphere, CO2, kind of rip it apart, release the oxygen, and then we keep the carbon, right? The tree keeps the carbon. But trees are actually carbon neutral, right? For the most part, scientists will argue 98%, something like that, right? The tree at the end of its life, it's going to fall over, it's going to die, and it's going to decompose right back into the atmosphere, right? Or we could burn it, right? What happens when we have combustion, right, with that piece of wood? We kind of have the initial spark to start the chain reaction, but then we take the oxygen. We need the oxygen for combustion, and then it bonds with the carbon in the wood, and we release CO2. Right? It all kind of goes round and round, a carbon cycle. And then, of course, our big issue is that the fossil fuels that we're traditionally using, it's not a complete cycle, right? We're taking stuff out of the ground that was buried there for millions upon hundreds of millions of years, and we're releasing it out really quickly. I don't think I need to beat everyone over the head with this kind of stuff. I think we all kind of know some of these themes. Just putting this out there, climate stripes, is a pretty neat way of actually visualizing annual change in temperatures and change in precipitation. This one only goes to 2020. The past 4 years are actually even worse. So it gets more red and more greenish teal as we go along. Just generally speaking about Ontario, our province, this is the province as a whole. Data here is from 2021. It's fairly similar now, not much has changed, but about 20% electricity, and then the rest is split about 40% natural gas and 40% petroleum and coal. And some people might ask, coal, we don't use coal anymore. We still use coal for industrial processes. And then important thing to note here, since we will be talking about air source heat pumps, and air source heat pumps use electricity, is that in our province, electricity is fairly low in greenhouse gas emissions. So this is the actual 2023 energy output, the whole year, what we actually used. Majority of it is nuclear, hydro. Believe it or not, we have close to about 10% wind in our province, and then the rest is filled by some smaller renewables, solar, biofuel, and then there's that gas section, which is usually around 10%. Focusing our shift now to homes, I'm going to talk a lot about air source heat pumps in single-family homes. So the reducing energy and carbon in homes, most of the energy that is used within a house is for space and water heating. Cooling is a tiny percentage. Here it says space cooling is 1%. It's about 5%, I think, in our province. It's a small amount. It might get higher actually with climate change, but it is a lot smaller. Needless to say that the space heating and water heating, which we traditionally use natural gas or fossil gas, i.e. methane. By the way, there's nothing really natural about natural gas. I hate the name, but we can discuss that some other time. So the real issue is that we have a necessity to reduce natural gas for space and water heating in homes. It needs to be cost effective, needs to be easy to do, and we do have the solutions. So there's a number of different ways in which we can reduce carbon in homes. I like to split it into kind of 2 or 3 buckets. One is building envelope. So what is your building actually made out of? Obviously, if you have a very leaky old house that has no insulation, that's going to be a poor energy performer, right? So that's what I mean by building envelope. It's your windows, it's your insulation, and it's your air tightness, air sealing. Then there's the mechanical systems. So what energy are we using? What energy are we putting into the house or taking out of the house? So air source heat pumps, geothermal, heat pump water heating, solar water heating. And then there's the last one, which is kind of behavioral change. It's a funny story. We did a study, looked at 6 multi-unit townhouses that were on electric heating. And one of the tenants was a real outlier. We replaced their electric heating with air source heat pumps. But they were so used to paying so much for electricity for their heating that they would always keep their place really cold. It was like 15 degrees, and they would just walk around with sweaters and heated blankets. So behavior is a very important part of it, and how we control and what we set our heating and cooling to. I want to get into heat pump. So this is where we're talking about the mechanical side, and this is what I'm going to focus on today and for the rest of my slides mainly. So John did a fantastic job kind of talking about this, the flow of heat from one place to another. I'm going to try to reiterate that with a few very simple examples. So heat pumps have been around for as long as refrigeration has. I think it's like over 100 years. So a lot of people have a difficulty with the concept of getting heat from really cold places, right? Like they say air source heat pump. Oh, there's no natural gas. Where's the heat coming from? It's minus 20 degrees outside. How are you getting heat out of that? So think about a fridge. So your fridge and freezer, actually checked mine earlier today. It was set at minus 18 degrees Celsius. But that box can actually generate heat. It's actually moving heat around. I have that picture here on the right. Does anyone recognize what that is? Maybe just give me a thumbs up or a heart emoji if you know how to do that. That's on the bottom of your screen in the reaction section. So that's the coil of an old fridge. That's what they used to look like for those younger people in the audience here that don't recognize the picture. And if you were to put your hand on that or near that while the fridge is kind of on and operating, you would feel heat, right? That's heat that's being removed from inside the box, right? That box is always trying to remove heat out of it, right? And saying the box, I mean the fridge and freezer. Think about it. We're always opening the door, letting some of that cool out or letting some heat in. It's not really well insulated. There's a gasket. And so the heat pump, the fridge, the refrigeration system is always working to remove heat from that space to make it cool. And as John said, one important thing to note is we don't really make cool. There's no such thing as cool. We are removing heat. So it's the absence of heat. Air source heat pumps can work in really cold temperatures. I've had an air source heat pump in my house down to the coldest temperature I've recorded is minus 23 with no backup system whatsoever. Air source heat pumps use basically the exact same components as air conditioners with some minor advancements. They have the capability to look exactly like air conditioners. And I'll go into certain types of systems and what they look like, and you'll see that they look exactly the same as a traditional furnace and air conditioner combo. And remember, it's really just a heat pump is really just an air conditioner that can go in reverse, right? Think about in the summertime, right? That picture of the two air conditioners there that are probably really familiar to you. You put your hand above that in the summertime when your air conditioner is running, and what do you feel? You feel heat, right? That is heat that was inside your house, right? You're removing that heat to make it cold. Same example as the fridge, right? In the wintertime, when you need heat, that heat pump goes in reverse. You can actually remove heat from outside, even in really cold temperatures, and then you're pumping it into your house, hence the name heat pump. You're pumping heat, moving heat from one place to another. This can be very efficient. We've seen some heat pumps that can operate to around a COP of 3 seasonally. That's 300%. So you're putting 1 unit of energy into it, and you're going to get 3 out. Again, because we're using that air, that heat that's in the air. And again, another thing to think about is that it uses electricity, so it's low in greenhouse gases. There are lots of different types of heat pumps, and this here is probably only a fraction of it. There's heat pump water heaters, which I will touch upon. I have one slide. There's heat pump pool heaters, which actually work great in our environment, considering that when it's hot outside is when we actually want to be in a pool. So we can just take that heat from outside, dump it into a pool. Ground source heat pumps, which John did a really good job of explaining. Air source heat pumps, which I will talk a little bit more about. There's heat pump clothes dryers too that are becoming more popular. So here's an example of 3 very typical systems that we see in homes. The middle one there is a split system. So this one is very typical for homes that maybe had electric baseboard heating and did not have central ducting, and they don't want to retrofit central ducting into their home. And so you could have a single split, which you have, again, focusing on the middle 2 pictures. The one on the left has the outdoor unit, and then you could see a few pipes. And then the one on the right, that's what the indoor unit looks like. The indoor units can look totally different too. They have ones that are very built in, that can be built into a bulkhead in the ceiling, and all you really see is like a vent or a grill. So there's lots of different options for those interior units. Moving to the right side of the screen, this is the system that pretty much, I would say, looks like most traditional Southern Ontario homes. You have, again, the 2 pictures on the right there, focusing on the left of the 2 pictures. You can see the box on the bottom, that's a furnace. You can see a box on top of that. That's where your A coil is, right? Normally, where you would have an air conditioner, inside you would have an A coil. Very similarly, a heat pump, an air source heat pump, has an A coil too. And so this system, although it looks exactly like, your traditional furnace and air conditioner, is actually a furnace and a heat pump. So with this system, the benefits are that maybe there's challenges in sizing the heat pump, or there's challenges in your duct sizes. And so you're able to size the heat pump to meet a majority of your heating load, in some cases 80% plus. And then the furnace would work in really cold conditions. Moving towards the left side of the screen, the 2 pictures there, this is a centrally ducted, all-electric, cold climate air source heat pump. There's lots of words there. So this, again, is very much like my home and many homes that I've seen throughout there. You have the outdoor unit pictured there, which I really like these, the Mitsubishi ones. They're nice and slim. A lot of these Japanese and Asian market products have that kind of slim vertical look, which I find is really nice compared to the traditional big ones that kind of sit on the ground. And then you have your air handler, which completely replaces the furnace on the very left-hand side there. So just very quickly, 3 different common systems. We've had a campaign that we ran for a couple years called Smarter Home Heating. And through that, we did a lot of different actual case studies. We looked at actual homes within Toronto and outside Toronto. Sorry if I keep saying Toronto. I hope I don't get anybody peeved being a Niagara crowd. But very similar climates, I think. So within these case studies, some of them went fully electric. So in this example, there was a homeowner that went fully electric. They were able to realize about $800 a year in utility savings. Keeping in mind that's changed a little bit now. So the blue circle is kind of where we're at now with utility rates. Back then, they were a few years ago, they were able to save a bit more. About $300 of that per year, that savings, was a reduction in cost due to their natural gas bill. So they were able to actually completely disconnect from the natural gas utility. And so they would see about a $300 savings per year just by not having to pay their natural gas bill. For those of you who don't know, you kind of pay, even if you use 0 natural gas, you're still paying. You're paying to have that connection, essentially. This home went all electric cold climate. They also had an air source heat pump water heater and some other minor retrofits as well. Moving on to hybrid systems, we did a study recently. We monitored 6 systems last winter. This was a hybrid study only. So this study focused on residents that kept their existing furnace and only replaced an aging air conditioner. And really promising results. If you can see from the natural gas consumption savings or natural gas reduction on the top right there, most of them, all of them essentially were able to realize greater than 80% natural gas savings. And a couple of them were able to see 100% savings as well. Utility savings, a lot harder to estimate, but it was roughly net. There was one that ended up paying a little bit more throughout the season, one that saved a significant amount throughout the season, but it's almost net. And again, these are hybrid systems. I have a very quick video here, just of a homeowner's experience with a heat pump. And please let me know if the sound is not coming through. Should be some piano there playing.
There's no
I'm
sound.
not hearing anything.
No sound? All right, I'm going to skip that. I apologize. I'll send a link to that video. We have a video series of about 5 videos that we did with different homeowners on their experiences with heat pumps. We also did a survey. We had a sample set of 22 homeowners. No unsatisfied homeowners. A large majority reported that they were satisfied or very satisfied with their heat pumps. And just a wrap up benefits of air source heat pumps. They can, in certain scenarios, be lower upfront cost. I know that there's some incentives right now. I mean, if you're electrically heated home, then yes, for sure, it's lower upfront cost. They move energy, they move heat from one place to another. They are way more efficient than traditional systems. They are quieter. I didn't go into this, but if you're used to that noise of an air conditioner in the summertime, that kind of that harsh startup. A lot of the heat pumps that are around now are what's called inverter driven or variable speed, and they actually have a lot quieter startup and are quieter overall. You can have better dehumidification with an air source heat pump. It can do heating and cooling. And again, you could lower GHG emissions and the potential to lower utility costs. One slide here on heat pump hot water heaters. So these are pretty nifty. They kind of look like standard old hot water tanks. But if you notice, they kind of have weird doohickeys, weird kind of sections on the top there. And the middle unit there that you can see in that picture on the right, you can kind of see a little circle there. There's actually a fan in behind there. And there's actually a heat pump. There's actually a little mini air to water heat pump, if you will, in that heat pump hot water heater. So what that is able to do is it actually takes heat from inside your living space and dumps that heat into the water tank. So it's creating hot water from the heat that is in your space. It may be best suited for unconditioned spaces or basement spaces. We have heard from individuals that have these, and we've done some testing as well. There is a bit of localized cooling around the area, and the manufacturers will recommend that you do have a certain amount of physical cubic feet, like physical space. So you can't put it in like a tiny closet. But it uses a lot less energy. So it's good for those who are really interested in electrification. It may be interested in completely removing their natural gas, is you could go this route and it's more efficient than straight up electric. Another point of reflection here, there's heat pump options for every home. Heat pumps we've evaluated are all mostly reducing utility costs given current utility rates. There's lots of other simple home improvement options you could do. I know we didn't get around them today. Air sealing is very easy, very, very easy to do. Get a tube or two of caulking and caulk around your windows, doors, and trim. And then the final thing, like if you're thinking of replacing your furnace or your air conditioner, please do consider a heat pump. There's lots of different incentives out there. I know we're getting on time. Just leave this up here for a second. I know that Mark is going to get into it with some details of what incentives are out there. There's this program, which is for low income. I would invite everyone to take a look at that table that has the number of people in the home and an income. If this is you, or if you're already in any of these programs that are here, allowance for survivors, what else? The LEAP, the Ontario Works or Disability Program. If you're already signed up for any of those programs or meet that income eligibility, then you can participate in this program free. And there's lots of really cool incentives that comes with that. There's the most recent Enbridge incentive program, and I have some examples of what the incentive amounts are. They are not as great as the older program that expired in February of this year, but at least it's something. And there's potentially more incentives coming next year. I know that federally they are looking at low income incentives, and Enbridge might have some involvement in that as well. That's it for me, and I hope that wasn't too much time. And I'm going to pass it back to Mark.
Yes, thank you, Gil. That was awesome. Very educational, informative. And I'll say again, if I was cut off at the very beginning, if you have questions for John or Gil, as per their presentations, please put it into the chat section below. Or if you want, you can wait till the end of the session. We'll also open it up for you asking questions verbally as well. I'm just going to go through. Whoops. There we go. I'll go through a couple other comments here. Just take a look at a few statistics before we move on. So you may find it comforting that heat pumps have been around, as Gil and John have said, for around the world for a long time, including in Canada. And there has been a marked increase of heat pump installations over the past few years here as well. And I understand that there's over 840,000 heat pumps as of last year in Canada. It's probably closer to 1 million now. And about half of those, or just under half of those, are in Ontario. While statistics for Niagara region are not readily available based on population and the region's mild climate relative to the rest of Canada, there's probably somewhere between 10 to 15,000 homes and buildings in the region that enjoys using heat pumps. And we actually know of a few. So some testimonials here from folks that live in the Niagara region. And when we open it up for questions later, Tim and Michael are both online and can answer your questions if you have questions of them as well. Essentially, the first two testimonials talk about electric air source heat pumps and are stating that they do, in fact, keep you warm in the wintertime and have eliminated their monthly gas bill. The third testimonial is very interesting. That is for a full electric ground source heat pump. And their electrical bill doesn't seem too much higher than mine, and they have no gas bills at all. At the bottom of the screen, I also added a Toronto resident in there as a reference because they do have an old Century home, and their heat pump keeps them, again, warm in the winter and has reduced their annual heating bill by about 30%. Something else I should mention as well is that I will be sending out a copy of these slides as well as the recording when this meeting is over or in the coming days. I'm going to skip a few slides here just for time's sake, but it is important to also understand the health issues associated with natural gas, the air pollution that is caused inside and outside of your home, and the not just premature deaths, but also the billions of dollars of healthcare that is wasted on air pollution every year. So Gil did talk about some of the cost savings, so I'm not going to go through all of these details. I will say that the Canadian Climate Institute has looked at the average Ontario homeowner home and said that we should be saving around 10,000 or more over the lifetime of the equipment with an air source heat pump, or even up to $24,000 for a ground source heat pump over the lifetime of that equipment. Of course, going forward, these cost savings vary based on government regulations and rebates, etc. Speaking of which, Ontario on those. We'll go through them again here, and we will be providing this slide that has the links so that you can click on these links on your own and look at the details of the programs and how to apply. However, I will say that depending on your income level, you may qualify for a free heat pump if you're replacing electric heating. If you don't qualify for that program, you can still receive a $5,000 rebate for an air source heat pump or $10,000 for a ground source heat pump, again, if you're replacing electric heating. If you're currently using heating oil in your home, then you can receive up to $10,000, and that's not a rebate. You get that up front to motivate you to switch to a heat pump, again, depending on your income level. So these are some decent incentives. Then there's also the interest-free loan that's available to pretty much all of us to switch your house over to a heat pump. There's also, I think Gil talked about this already, the rebates for through the Enbridge program. It's about $3,000 for a ground source heat pump, about $2,000 for an air source heat pump, and $500 for a heat pump water heater. I think it's interesting to know too that our federally funded Greener Homes program supported approximately 165,000 homeowners across Canada over the last 3 years. So we're hoping that this program returns at the end of next year, but that all depends on the next federal election. I also listed if you're interested in looking further into obtaining a heat pump, the slide deck that I'll share will give you a number of companies in the Niagara region that can help you out. We're hoping that you found this webinar interesting and educational, but also hopefully motivating. So if you've been motivated by tonight's webinar and want to take action to help persuade our governments to do more to facilitate the inevitable green energy transition that's going on around the world, we'll ask you to sign these petitions. The first petition is from an environmental group called 350.org. The second is from Greenpeace Canada. And then the third is from another environmental group called Stand.Earth. They're great organizations to get familiar with. We've also provided a number of links if you want to do some more reading on your own, as well as some calculators to see if how much savings you can obtain by switching to heat pump in your home. Those are the ones that are highlighted in bold. So with that, I'll ask if anyone has a question to put it into the chat, and we'll do our best to get to them all. As I mentioned earlier, John is here, Gil is here. We also have Tim and Michael online with their systems in the Niagara region. If you prefer to ask verbally, you can always raise your hand in the function at the bottom of the screen. Herb, are you able to share any questions that anybody has asked?
Yeah, no one's got any questions yet. If you want to put up your hands. Oh, go ahead, Tim. There we go. Just funny, I was about to ask Tim for a testimonial anyways, so he may as well lead us off.
I have a question for Gil. When I did my transition, heat pump hot water heaters weren't readily available. So I just wanted to comment that I put in an on-demand electric water heater for my home. There's just two of us in our home, and it serves us great. So, and the great thing about that is it only uses electricity when it's on. The only bad thing about that is if you have a teenager, it might run for a little while.
Tim, which brand was yours? Do you know?
It's a Ream.
Ream.
Yeah.
Right.
Like I said, when I did the transition, the heat pump water heaters weren't readily available.
And do you notice any extreme kind of electric utility bills? I know a lot of people are like, oh, electric hot water, it's so expensive. Just wondering if you can comment or if you see a difference or what the difference might be.
No, there's nothing that I see that's extreme about it. It replaced my gas water heater, obviously, and even in the gas water heater, it had electricity to ventilate it. So, no, we're quite happy with our electric billing. Up until before I put the solar up, we were averaging about $194 a month, and that includes running my EV.
Did you disconnect from the natural gas grid?
Yes, yeah. Once we had everything up and running, we disconnected. So I only have the one utility. So you mentioned the savings there earlier.
That's great. Wonderful to hear your experience, Tim.
Thank you.
Liz, you had a question?
Yeah, I see that my question's similar to what Susan has in the chat. So I have a house that was built in 1900. It's got a gas furnace. It doesn't have any duct work. We don't have air conditioning. And we asked around a few years ago about whether we could get a heat pump system for a house like this that's dependent on hot water rads, that the water's heated by the gas furnace. And we were told it wouldn't be practical in our situation. What would you say to that?
I could maybe field this. Your existing system is hot water rad?
Yeah.
Okay. So two approaches that are doable. So air to water heat pump, not the number two, but air TO water heat pump, is the technology name that you should be doing some Googling. And as of recent, there's a lot more options than there were just a few years ago. Um, the challenge there, so the system might be a bit expensive. The other challenge is that you're not going to have any cooling, and so I know a lot of people like their rads or they have in-floor heating and they want to keep it in-floor. I understand it's very comfortable. But the other option would be a multi-split system, similar to that middle example of the three that I showed. In which case you wouldn't be using your rads, you'd totally be using a split heat pump system, but it would be able to provide you with cooling now as well. So those are two options, air to water and multi-split heat
So
pump.
one second question, does it make a difference what the size of the area is? Because it's a pretty big house. So I think it's 4,000 square feet. So does that make it impractical or not?
Not impractical. There are multi-split heat pump systems that I believe go up to 5 ton, and depending on the heat and cooling, well, heat load mainly of your house, that might be doable. You could always put two outdoor units outside that can also be staged and kind of talk to each other. I think that some manufacturers have that capability as well. I would look into both scenarios, the air to water and the multi-split, and then kind of make your decisions there because they are a bit different.
Okay, thank you.
Yeah.
Awesome. Thank you, Liz and Susan and Gil. There's the next question. I suspect I know the answer to this one, but John, this is for you regarding the new Niagara Hospital that's being built, that they're in process right now. Do you know, did they ever consider geothermal energy ground source for that one?
I really don't have any insight into that one, unfortunately. I would hope so. What we're seeing a lot is a lot of more business as usual. I'm not saying that's what they're doing, but I just don't know. But we're just kind of adding to the retrofit pile, so to speak.
Yeah.
So whatever costs are being incurred now to build that thing, if it's using fossil fuels as the primary source of heating, it's going to be much more expensive to retrofit that at the future than it would be to get it right the first time. So I'm hoping they are looking at it, but I personally and professionally, I don't have any insights into the Niagara Hospital.
Yeah, from what I know, and I think I'm right about this, I know that they're going to be using natural gas. There is a wastewater treatment plant that will be built kind of at a development close by there. So they're doing things in the wrong order. They can't, and the region is exploring using that wastewater treatment plant for district energy.
That is a great use. There's a couple examples of this happening in Toronto
Yeah.
and Mississauga. So, and then huge projects out in BC. We're advising on one right now for a First Nations development
False
in
Creek.
partnership. Yeah, exactly. The Senok development. So it's all very doable. But again, I think it's the people kind of problem coming to bear here, compounded with, I think decision makers maybe not knowing what their options are. So, but they have schedules and they have budgets and they have to there's a lot of priorities pulling these decision makers in lots of different directions. So
Yeah.
I don't
Yeah.
blame them, but it's just going to be a lot more expensive when they eventually get to that point.
I don't blame them for not knowing. I do blame them for not wanting to know.
Fair.
But you are a very gracious person. I really like how you speak to your audience and to your yeah, when you know that people need to be educated, you do it very, very well.
Appreciate that. Thank you.
John. Mona has another question, and yeah, whoever wants to field this one, go right ahead. Wondering where we can find reliable information about the qualities of various heat pump brands and the companies that install them. I mean, I know that all the major brands are making the heat pumps, um, and I had wanted to put a Mitsubishi in our home, except it was too tall for our basement. We've got a 100-year-old house. Um, but yeah, what can we talk? Gil, can you maybe talk to the reliability of heat pump brands?
Um, I mean, I wouldn't want to single anyone out. There are brands that have been around for a really long time and they have a good track record. A lot of them are the Japanese inverter-driven ones, so like LG, Daikin, Mitsubishi, GE,
LG?
LG, yeah. Um, those systems commonly come with a premium, a price premium. Um, there are surprisingly lots of heat pumps now that are very affordable that have very good performance. I cannot speak to the longevity of them. I know that there's like Move Air, which is, I think, a rebranded Gree as well. They are very affordable and the performance is very good. They don't have a long track record in North America, but they've been around in China for 30, I think 40 plus years. Um, it's hard to say. I mean, do a bit of research, ask the neighbors what they have. Um, yeah. And it's equipment, like it once in a while people just end up with a dud, so
Mhm.
I could say, X company is great, and then your neighbor tells you no, they suck. But I mean, just like once in a while you get a car and it's a lemon. I suppose that could happen with a lot of different technologies. But I mean, I always say, life of, 15 or so years, lifespan is what I kind of like to say.
Yeah,
Uh,
what brand do you have in your house?
I have a Daikin,
Okay.
Daikin.
Yeah. So Mona's looking for something other than Daikin or Mitsubishi. But we have a crane in our house, and now it's been a year and a half, and very happy with it. Um, yeah, really. One thing that we really like about ours is it seems that heat pumps do not dry out the air nearly as much as a gas furnace does, and so it's just more comfortable. Um, Tim, you wanted to jump in on this one, I think. What kind of
Yeah.
a heat pump do you have?
So we installed Rude through Montgomery Gas here at Port Colmar, and Rude is just another name for Ream.
Mm,
Uh, and what's really important when you get it installed is it's right sized for the home. Um, our home is 1,200 square feet. We were running with a ton and a half before, and the installer said, "Oh, we needed to go up to 2 tons." And uh, a rough rule of thumb is a ton for every 500 square feet. So you can understand why we went up to 2 tons. At any rate, been very efficient, no issues. They have a 10-year warranty. Most of them come with a 10 or a 12-year warranty. So really no worries for that amount of time usually. We've had ours serviced every second year. They don't seem to think that you need to do it every year because it's not as complex as gas. And so servicing every 2 years as opposed to one is a bit of a savings too.
Awesome. Thank you very much. Mona, in the chats, Michael Hendricks has added to our comments. So he's got a website there that he recommends you look at. We've got a
Here,
couple more questions yet. Are we ready to keep
someone
on?
someone had their hand up there, the 7TW
Yeah, there's also a
BMW.
few more. There's also a few more questions in the chat here.
Okay.
I saw Seven's hand too. Mark, how much longer do we want to go here with some of these questions?
Well, people want to continue to stay on. We'll keep going.
Yeah, so
Liz, I don't think it's going to
I'm
time out.
I'm happy to stay. I'm happy to
Pardon?
stay. I'm
Thank
happy
you.
to stay for another 15 minutes or whatever.
Yeah,
all
it
right,
won't time out,
so
Mark, so go ahead.
all
Yep.
right, so we'll ask Annette and then Susan and then 70W. All right. So Annette's wondering about switching from fossil gas to heat pumps, to a heat pump to heat and cool our home. What type of backup do you recommend if there's a power outage?
I'm going to let Gil answer that, but I will say that your gas furnace also doesn't work when there's a power outage. So,
Yeah, I would echo that. A lot of people seem to come up with that, question. It's like, oh, well, what happens if the power goes out? Well, your furnace won't work either. But in terms of capacity and backup, I know a lot of times HVAC techs and contractors, installers will recommend you have a backup for your air source heat pump. Most of these are straight electric backup. It's just a little coil that lives within the indoor part of the heat pump, the what was a furnace part. And usually you don't even see them, and the costs are so low. They're just included in the cost of the entire system. Um, I my system, fully cold climate, um, ducted air source heat pump. I have a backup electric coil in my system, and it actually was never set up. So I have the wires going to the breaker panel, but I don't have it connected. I don't think I'll ever need to use it, but my system is a little bit oversized. Um, so yeah, I mean, one thing, if your power goes out, you're not going to have either or. So do have an emergency preparedness plan, emergency preparedness kit. That is probably key. And then if we're talking about backup in terms of capacity and sizing, most HVAC contractors will take care of that.
All right, thank you. Susan's basically wondering if she heard right. Is an air to water heat pump the only option to use for hot water rads? But no, you had two options, right? You suggested air to water heat pump or a
Multi-split air source heat pump.
all right, here, I'm just going to put that into the chat. Multi-split air.
And that's just for clarity. Whoop, I've lost you. I'm gonna share again and show you what that looks like because I have it up here somewhere. Hopefully I don't take up too much time. Am I here? Can you see me?
Yeah, we hear you.
Okay, so that's this middle two pictures here, right? So that's what your outdoor unit would look like, and then you have a number of different pipes going inside your house, and that's like the number of indoor heads. And this, depending on your house and what the inside and outside looks like, you could make this cleaner. You could have only one kind of duct go inside, and then you have to do a whole bunch of interior work to kind of move it along. And again, this interior head that you see there up above those double doors or windows, that can look different too. Like they have ones that are like that are pretty big, or they have ones that are, if you do a bit more work, can be buried into like a ceiling or a wall or a bulkhead or something like that. So multi-split air source heat pump.
Great, thank you. Gil, again for you, which side of the house is best for a heat pump?
The side of the house that works best for you. I don't think, like, in terms of thermodynamics, there's not much, like in terms of the science behind it, there's not much of a difference if, it's fully in the shade or fully in the sun or being blocked by wind. John, maybe you know more of the engineering of that, but from what I know, there's not much of a difference. It's what's going to work for you and your house and what your installer needs to work with too. You might tell them I want it here. They might tell you no. Yeah, that's what I have for that.
Yeah, I would second that. Depending on the make and model, noise might be the bigger consideration if it's not the quietest of models. The other thing is you want to make sure it's off the ground, because if you have a snow drift up against it, that you're not going to get a lot of airflow through that thing. So, but I don't think the side of the house is going to affect the performance in any meaningful way.
Awesome. Thank you, John. So the next question is, I don't know who wants to field this. Liz, you might have something to say to this. Can anything be done if a person is in a long-term rental agreement and they would like to switch from gas to an air pump? I don't think that a renter can do anything about that, but does anybody know any different?
I think it depends on your relationship with your landlord or however that may go. The challenge, the danger of that is, if you are a renter, and you end up investing in the mechanical system or anything within the home or apartment or whatever it may be, there's a chance that for some reason or another, your landlord may want to sell the house a year later or who knows what. So that's just the challenge of those, split incentives or splitting the cost there.
Sorry, Gil, just to interrupt though, I think the question might be though if you're renting your furnace, which is the case for most people.
Oh,
So I can
okay,
give you guys an example, but it's a hot water tank. It cost me $1,600 to get out of my rental. So it's based on the age of the tank.
So you basically have to pay out the company that you're renting the equipment from.
That's correct.
So that's typically why the recommendation is for when you need a new air conditioner, when you need a new furnace, instead of getting a new furnace again on a rental agreement, then switch to a heat pump. That's the most economical way to do it.
Okay, my apologies. I misread that question, misunderstood it. But thank you guys for catching that. And also 7TW, I skipped ahead. So go ahead and ask your question, please. And you're still muted, sorry.
There. I just wanted to say thank you and 7TW here. My husband Dave and I, we live in a small bungalow in St. Catharines, and we are moving next year onto 3 acres with our kids. They're in an existing home, and we're going to build like a little granny suite on the side. So Tim, you really nailed a few great questions I had. It's about 1,100 square feet. So your 1,200 square feet, 1 ton basically for 500 square feet for the heat pump was really, good information. And all of these links. I mean, we've got so much information. This is awesome. It's a little bit overload right now, but Herb, you've got one. Tim, you've got one. You're in Port Colborne, and so we'll be picking your brains and reading. So we'd like to pursue this. I just wanted to say, I guess we'd just start with all the links, and Gil too, that you've given us. I guess that's the best way to start.
Are you designing a totally separate suite?
Yes, and we wanted really interested in making it, as totally as energy efficient as possible. I mean, solar heat pumps. It's a project that I would like to do as much as that as possible. It's always interested me. So
Yeah, I would say work with your architect or designer, unless you're the one building it. In which case, if you're the one drawing, if you're the one drawing and submitting the drawings, I would take a look at code and then try to within your means go above as much as you can.
yeah,
And if you're the one designing it, maybe worthwhile, like if you're the one submitting drawings, maybe worthwhile trying to get a HVAC design
mhm,
um, to properly, like usually an architect would know what that is. But if you're the one submitting drawings, um, they can be a bit expensive. You could also do it with energy auditing software, but I would really recommend an HVAC design. Or another term you could look at is F 280, F like Foxtrot dash 280. That is a federal design software for evaluating heating and cooling loads, and also designing as well, like the location of ducts, sizing of ducting.
okay,
I
Great.
hope that helps.
Thank you very
Yeah.
much. Yes, it does.
great.
It was a great evening. Thank you.
You're welcome, and I think if you could find a local on the list that I provided earlier, which I'll be sharing that, if you can find a local service provider for heat pumps, you might want to talk to two or three of them and see what they say in terms of the best options for you.
Right.
Yeah,
Okay.
we'll do that. Thank you.
Awesome.